Hello everyone and welcome. Imagine waking up in the middle of a scorching August heat wave, with millions of air conditioning units humming across cities, industrial plants operating at maximum capacity, and electric transport drawing steady power from the grid. Now imagine that suddenly, without a mechanical explosion or an enemy cyber attack, your nation's single most critical power plant loses more than 80% of its total electrical output. This is not a dystopian fiction. It is the real scenario that unfolded in Hungary in August 2026. Across Europe and indeed across the entire world, we have spent decades building our power systems around a bedrock assumption that large, centralized thermal and nuclear power plants represent unshakable baseload reliability. We treated them as immutable pillars of the grid that run quietly in the background, impervious to the weather outside. But climate realities are rewriting the laws of energy security in real time. Today, we will unpack the dramatic story of what happens when a river-fed nuclear giant is brought to its knees by drought, how an aggressive surge of solar power stepped in to prevent immediate catastrophe, and what profound lessons this crisis offers for engineers, grid operators, and policymakers navigating a warmer and far more volatile world. Let us begin with a provocative question that every utility executive, power planner, and grid operator must confront today. What happens when your most dependable power source suddenly disappears? For nearly half a century, the power industry operated under the steady doctrine that thermal and nuclear power plants are baseload champions, completely independent of weather variability. When the wind refused to blow or when dark clouds blocked the sun, grid controllers could always lean with total confidence on the heavy spinning turbines of centralized nuclear reactors. But what happens when the environmental foundation upon which those giant stations depend, the steady cool flow of fresh water, simply vanishes beneath them? This fundamental question shifts our perspective from simple component reliability to deep systemic vulnerability. When a single anchor asset falters, the shockwaves travel instantly across the entire transmission network, testing every substation, transformer, and market mechanism. As we examine this case study today, keep this core dilemma in mind. If baseload can fail abruptly due to climate stress, how do we fundamentally rethink grid security? To understand the gravity of the August 2026 crisis, we must first look at the cornerstone of the Hungarian power sector, the Paks nuclear power plant. Situated directly on the banks of the Danube River, roughly 100 kilometers south of Budapest, Paks is not merely one power station among many. It has historically served as the beating heart and central spine of Hungary's electrical infrastructure. Comprising 4 Russian-designed VVR-440 pressurized water reactor units commissioned in the 1980s, the facility has consistently delivered roughly 2 gigawatts of zero-carbon baseload electricity with outstanding operational uptime. Generations of Hungarian engineers and system planners have viewed Paks as an unassailable fortress of energetic sovereignty. Its steady humming turbines have anchored grid frequency, dampened voltage fluctuations, and sheltered the national economy from the wild price swings of imported fossil fuels. Paks was built with the premise that large-scale nuclear power provides absolute certainty in an uncertain world, operating uninterrupted day and night, summer and winter. Just how vital is Paks to the everyday life of Hungary? Take a look at the striking figure on this map. Nuclear energy historically generates approximately half of all electricity consumed across the country. In many operating months, that share climbs even higher, supplying upwards of 55% of national demand. Consider the implications of that centralization. From the bustling industrial manufacturing corridors of Győr and Debrecen to the electrified rail networks and the residential towers of Budapest, 1 out of every 2 light bulbs, medical devices, and factory assembly lines has been kept alive directly by the steady fission of uranium atoms at Paks. This massive concentration of supply meant that Hungarian energy policy became deeply anchored around this single geographic coordinate. When a country relies on one single facility for half of its lifeblood, high availability is not just an economic target. It is an absolute matter of national survival and public order. For decades, the promise of nuclear power has been encapsulated in 3 simple characters: 24/7 power. In the pristine turbine halls and control rooms of modern nuclear stations, pristine machinery operates with relentless precision. Unlike wind turbines that slow when the breeze dies down, or solar panels that sleep through the night, nuclear reactors provide steady, deterministic, and dispatchable megawatt hours around the clock. That predictable baseload is precisely what allowed 20th century industrial economies to thrive. It gave operators the confidence to run continuous smelters, automotive plants, and heavy manufacturing without worrying about the weather forecast. But embedded within that promise is a critical caveat that was too often overlooked in historical risk models. 24/7 power remains guaranteed only until something fundamental in the surrounding natural environment changes. When the hydrological operating conditions of the plant are altered by extreme planetary shifts, even the most formidable nuclear fortress becomes hostage to the climate. Let us examine the basic physics and engineering constraints that make nuclear power inextricably linked to surface hydrology. As illustrated in this system diagram, a nuclear power plant does not run on nuclear physics alone. It runs on an immense and continuous circulation of water. Inside the reactor pressure vessel, fission heats water to create high-pressure steam that drives the turbine generator. However, once that steam passes through the low-pressure turbine blades, it must be rapidly cooled and condensed back into liquid water so it can be pumped back into the steam generators. This condensation cycle requires an astonishing volume of cold cooling water drawn directly from the adjacent river via massive intake channels. That water absorbs tremendous amounts of waste heat across thousands of condenser tubes before being discharged back into the river system. A standard 2-gigawatt nuclear facility like Paks requires upwards of 100 cubic meters of river water every single second. Without an uninterrupted flow of sufficiently cool water, thermodynamic heat rejection becomes mathematically impossible, and safety thresholds are violated instantly. In the summer of 2026, the unthinkable unfolded across Central Europe. The mighty Danube River began to wither. Following a winter of record-low alpine snowfall and consecutive months of blistering, rainless heat waves across the Danube catchment basin, the river's discharge rate plummeted toward historical absolute minimums. The majestic waterway, celebrated in poetry and relied upon as Europe's primary industrial artery, was reduced in many stretches to an exposed corridor of cracked mud, sandbars, and shallow channels. For the Paks nuclear power plant, this was not merely an aesthetic tragedy, it was an operational catastrophe. The physical water level dropped dangerously close to the minimum engineering intake heights required by the heavy cooling water pumps, threatening cavitation, silt ingestion, and severe pump damage. Simultaneously, the sluggish, shallow river water baked under relentless 38 degrees Celsius sunshine, sending water temperatures soaring past critical environmental and technical thresholds. Here we see the dramatic visual comparison of what climate extremes look like from above. On the left, we observe the Danube River under normal hydrological conditions, a deep, wide, rapidly flowing body of cool water easily capable of absorbing thermal discharges and providing ample hydraulic head for heavy industrial intakes. On the right is the grim reality of August 2026, extreme low water levels exposing vast expanses of the riverbed. Under national environmental regulations designed to protect fragile aquatic ecosystems, nuclear power plants are strictly forbidden from discharging cooling water if the downstream river temperature exceeds 30 degrees Celsius, or if the thermal delta threatens mass fish die-offs. In August 2026, the incoming Danube water was already approaching 27 to 28 degrees Celsius before even touching the condensers. The plant faced a brutal double constraint: insufficient water volume to operate pumps safely, and zero thermal headroom to reject heat into the river without triggering an environmental and ecological disaster. This brings us to the acute mechanics of the cooling bottleneck. When river levels collapse and ambient water temperatures surge, a thermal power plant enters a compounding operational crisis. First, the reduction in hydraulic pressure forces operators to throttle intake valves to prevent sucking abrasive river sediment into the delicate heat exchangers. Second, the fundamental laws of thermodynamics dictate that when cooling water is warm, condenser vacuum efficiency degrades, causing turbine back pressure to rise and sharply eroding overall plant efficiency. Third, and most crucially, strict statutory thermal limits force reactor operators into mandatory power curtailment. In order to keep the downstream thermal plume below legal environmental limits, plant engineers have only one lever left to pull. Insert control rods into the reactor core, dampen the nuclear chain reaction, and drastically dial down electrical generation. What was engineered as an unshakable 2,000 megawatt powerhouse suddenly becomes constrained by the biological and physical limits of a drying river. The consequences unfolded with terrifying speed across the Paks reactor complex. Unit after unit was forced into aggressive power throttling. One reactor was taken completely offline for emergency maintenance to clear intake screens and manage thermal stress. The remaining units were throttled down to fractional capacities. As the nocturnal aerial view illustrates, 3 out of the 4 reactor units were reduced to a fraction of their nameplate generation, leaving only one unit running anywhere near full output. In the National Control Center of Mayar, Hungary's transmission system operator, warning alarms began to flash. Over 1,500 megawatts of rock-solid, zero-carbon baseload electricity evaporated from the national supply stack within a matter of days. In standard utility planning, a loss of this magnitude is categorized as an extreme N-1 contingency that threatens widespread cascading blackouts if replacement power cannot be mobilized within minutes. When the final tally was calculated during the peak of the heat wave, the headline number sent shockwaves throughout the global nuclear and energy engineering communities. Paks' nuclear output was down by more than 80%. Think about the magnitude of that collapse. An infrastructure asset that had reliably generated half of an entire nation's electrical energy for decades was suddenly reduced to a mere trickle of its installed capacity. In boardrooms, trading floors, and ministry offices, the narrative that nuclear energy is immune to climatic forces shattered in an instant. This dramatic 80+% reduction proved conclusively that in an era of accelerating global warming, water security is energy security. No thermal power plant, whether nuclear, coal, or gas, can generate electricity in a vacuum without considering the planetary ecological systems in which it is embedded. Yet while nuclear generation was plunging toward near zero, what was happening on the demand side of the equation? As this slide powerfully emphasizes, the demand didn't disappear. In fact, it did the exact opposite, skyrocketed to near-record summer levels. Across the metropolitan area of Budapest, where over 2 million citizens live and work, air conditioning units ran at maximum blast to fend off lethal urban heat island effects. High-tech manufacturing plants, pharmaceutical cleanrooms, and electric bus fleets continued to pull immense loads from the grid. In hospitals, commercial centers, and municipal water pumping stations, uninterrupted power was an urgent question of life and safety. Energy consumers do not care if a river is dry or if a turbine condenser is overheating. When they flip a switch or plug in a life support system, they expect absolute voltage and frequency stability. The gap between plunging baseload supply and soaring national demand had become a gaping chasm. In the high-stakes world of electric transmission and grid physics, there is one non-negotiable physical law: power has to come from somewhere. The power grid has virtually zero intrinsic tolerance for imbalance between generation and consumption. At every single microsecond, supply must match demand with flawless precision, or frequency collapses and the entire synchronized European transmission network begins to trip offline. With Paks crippled, Hungary faced an existential energy challenge. Could neighboring countries export enough emergency electricity through cross-border interconnectors without driving regional market prices into thousands of euros per megawatt hour? Could domestic gas-fired peaker plants ramp up fast enough without exhausting fuel reserves? The system was pushed to the absolute brink of catastrophic load shedding, searching desperately for a source of power that could instantly fill a 2-gigawatt void in the middle of a blazing summer afternoon. And then, right at the precipice of disaster, something remarkable occurred. Solar surged, the very meteorological phenomenon that was choking the nuclear plant. The relentless, cloudless, baking summer sun that dried up the Danube became the ultimate salvation of the Hungarian power system. As high-pressure atmospheric domes trapped blinding sunlight across the Pannonian Basin, photovoltaic panels across the country began to generate power at unprecedented record levels. Fission gave way to fusion as energy radiated from our star 93 million miles away was captured directly by silicon semiconductors across the Hungarian countryside. In an astonishing demonstration of natural complementarity, solar power peaked at the exact moment when air conditioning demand was soaring and nuclear generation was experiencing its worst historical curtailment. This solar rescue was made possible because, over the preceding 5 to 7 years, Hungary had quietly executed one of the fastest and most aggressive solar expansions in all of Europe. Driven by progressive feed-in tariffs, corporate power purchase agreements, and massive utility-scale investments, the country blanketed former agricultural lands, brownfields, and industrial rooftops with state-of-the-art photovoltaic arrays. By 2026, Hungary's total installed solar capacity had surged past 6 gigawatts, a massive fleet capable of generating immense volumes of clean electricity under clear skies. When the nuclear reactors were throttled back, this vast distributed solar fleet was fully energized, primed to pump thousands of megawatts of direct current into inverters, stepping up voltage onto the transmission grid and fundamentally transforming the national generation landscape in real time. By the time the clock struck 12 noon, the operational profile of the Hungarian power grid had undergone a total revolution. At midday, solar photovoltaics became the largest single source of electricity in the country, completely overshadowing what remained of nuclear and conventional thermal generation. Fields of gleaming solar panels spanning hundreds of hectares were capturing photon flux and delivering high-voltage clean electricity directly into the national grid. For the dispatch engineers at MAVIR, watching the real-time supervisory control and data acquisition displays was a surreal experience. The historic baseload anchor of the nation had receded into the background, while decentralized renewable energy was suddenly carrying the heavy industrial and commercial load of an entire nation on its shoulders. Let us quantify the sheer scale of this solar achievement. During peak midday hours throughout that critical week in August 2026, the national solar fleet generated over 55% of Hungary's total instantaneous electricity consumption. Think about the symmetry of that statistic. In normal times, nuclear provides 50% of Hungary's power. During this extreme climate crisis, solar rose up to generate over 55%. Not only did solar generation cover the domestic deficit, but at certain peak hours, Hungary actually transitioned from a distressed energy importer into a net exporter of green electricity to neighboring Central European grids. This massive influx of solar power kept power prices stable, suppressed volatile wholesale spot markets, and prevented what would have otherwise been mandatory rolling brownouts across major industrial zones. As this system integration diagram beautifully demonstrates, solar successfully helped fill the dangerous supply gap. The recipe that preserved grid stability was a dynamic balancing act. Reduced nuclear generation formed a lower base. The massive solar surge provided the vast bulk of midday energy, while flexible cross-border imports, domestic hydro, and peaking plants filled the remaining margins. Total demand was fully served without disconnecting a single factory, home, or hospital. This episode proved beyond doubt that renewable energy is not merely a decarbonization tool or an ideological luxury. It is a frontline resilience mechanism capable of defending national energy security against catastrophic climate disruptions to conventional thermal infrastructure. However, every experienced power engineer in this room knows the fundamental physical limitation of solar energy. Then, the sun set. As the clock moved past 6 in the evening and the sun dipped toward the western horizon, the golden light faded, and solar output plunged swiftly towards zero. Photovoltaic cells do not care about grid demand. When photons stop striking the silicon wafers, electricity production ceases instantly. Within a narrow window of just 90 minutes, over 4,000 megawatts of solar generation vanished from the Hungarian grid. Under normal operating conditions, an evening drop in solar is easily managed by steady nuclear baseload. But remember, in August 2026, Paks was still locked in an 80% curtailment due to the hot, shallow river. The grid was about to face its most dangerous trial. Take a very close look at this chart because it illustrates the ultimate nightmare scenario for modern power systems, the extreme evening ramp. The yellow line shows solar generation plummeting off a cliff from 100% down to zero between 4 and 8 o'clock in the evening. Meanwhile, look at the blue line. National electricity demand is actually climbing, reaching its absolute peak at 8 o'clock at night as millions of families return home, turn on household appliances, run cooking stoves, and crank up air conditioning against the persistent evening heat. Solar disappears, demand doesn't. This creates a colossal net load deficit that must be filled by other flexible assets with blistering speed. If a grid cannot ramp up thousands of megawatts of replacement power within minutes, system frequency collapses, automatic under-frequency load shedding kicks in, and entire cities go dark. How does a modern power system survive this brutal evening transition when its primary baseload plant is offline and the sun has gone down? The answer is unambiguous. The grid needs massive, multi-dimensional flexibility. As shown on this slide, resilience is not built on a single silver bullet, but on an ecosystem of flexible capabilities. First, utility-scale battery energy storage systems must charge during cheap midday solar peaks and discharge rapidly during the evening ramp. Second, regional interconnectors must import hydropower from the Alps or wind power from the North Sea. Third, fast-ramping flexible generation, such as advanced combined cycle and open cycle turbines, must fire up instantly. Fourth, demand response programs must incentivize industrial consumers to shift heavy loads away from the evening peak. When nuclear cannot cool and solar cannot shine, flexibility is the only currency that matters. We must also understand that the crisis in Hungary was not an isolated, freak event confined within national borders. The Danube River flows across nearly 3,000 kilometers, traversing 10 European nations before reaching the Black Sea. As shown on this map, the drought of 2026 became a transnational crisis that spread down the entire river corridor. Downstream from Paks in Bulgaria, the Kozloduy nuclear power plant faced identical hydrological bottlenecks, with river levels dropping and thermal cooling discharge permits threatened. Simultaneously, river barge traffic transporting coal, biomass, and essential industrial cargo ground to a complete halt, disrupting fossil fuel supply chains across the continent. Hydroelectric dams along the Danube and its tributaries saw generation drop by 40 to 60%. When an entire river basin suffers from severe climate stress, the interconnected vulnerability of the entire regional energy system is exposed. This brings us to the profound, overarching question that will define energy infrastructure planning for the next half-century. Can our power systems handle a hotter, drier world? For more than a century, civil, thermal, and electrical engineers designed energy systems around the historical climate records of the 20th century. We calculated 100-year flood levels, historical drought baselines, and maximum water temperature records, assuming that the future would look roughly like the past. That stationary climate baseline is dead. The World Meteorological Organization and climate models confirm that heat waves will be hotter, droughts will be deeper, and river temperatures will routinely surpass historical records. If our entire baseload thermal fleet, nuclear, coal, and gas combined, was built assuming an endless supply of freezing river water, we must fundamentally reconstruct our risk models, cooling technologies, and system architectures for a radically harsher planetary reality. The ultimate conclusion of the Renewable energy analysis is crystal clear. True grid resilience comes from diversity, never from overdependence on any single technology. No single energy source is completely infallible. Nuclear provides massive zero-carbon baseload, but it requires vast water resources and lacks rapid dispatch flexibility under thermal constraints. Solar delivers abundant, low-cost power during scorching daytime heat waves, but it vanishes entirely at night. Wind can generate through darkness, but it faces seasonal lulls. As this integrated architectural diagram illustrates, a resilient power system must orchestrate nuclear, solar, battery storage, robust high-voltage transmission interconnectors, and flexible fast dispatch generation into a harmonized, self-healing network. Diversity is nature's ultimate survival strategy, and it must become the defining design philosophy of the 21st century power grid. To conclude our presentation today, let us reflect on this fundamental transformation in power systems thinking. The future grid has to expect the unexpected. For decades, the energy sector measured reliability through a narrow, localized lens. What is the capacity factor and forced outage rate of an individual power plant? Today, in an era of climate extremes and decentralized renewable generation, that definition is obsolete. Reliability is no longer just about how an individual power plant performs in isolation. It is about how the entire interconnected system responds, adapts, and recovers when a critical component inevitably fails. The August 2026 crisis in Hungary demonstrated that when an unprecedented climate disruption crippled a national nuclear anchor, it was the diversity of the system. The sudden surge of solar power, robust grid interconnections, and flexible balancing reserves that prevented disaster and kept the lights on. As we build the grids of tomorrow, let us design not for idealized laboratory conditions, but for a dynamic, volatile world, creating resilient, diverse, and flexible energy systems capable of weathering any storm and outlasting any drought. Thank you very much for your time and attention.